Okay, in here, we're just gonna look at the experimental calculation or determination of the metacentric height that is denoted by GM in this kind of like the picture. So if you look at this picture, so we want to just see how we can experimentally calculate this one. You know, in the pontoon, the floating body that we have a juggy weight. The juggy weight is located somewhere over the a pontoon, for example. We can just denote it by this one, for example. If that kind of like the juggy weight, it just moved from the center line with the distance of like the dx, for example, dx or delta x in this figure, towards the side. And if we have that one, and imagine that vertical weight distribution is unchanged, so we have like the same vertical distribution. So the center line, or the center of the gravity from the G that was original one, moved to the new position G star. So we're just gonna have like a G to G star, and we have like a tilting, or the tilt of angle of tilt is equal to delta theta, like this one. And we can just measure this one by pendulum here at the bottom of this pontoon in the laboratory experiment. If you're just gonna take the moment around like the point C, we can just easily write the GG star as a lever arm times the total weight. If the total weight is the capital W, is equal to the WG, or the weight of the jug weights, times the delta X. The delta X is a lever arm, and WG, this one, is equal to GG star times capital W, if you're just going to moment around this point. And if you just rearrange like the GG star, we can just write this one. GG star is the ratio of the WG, is the jug weight, over the total weight, times the delta X. Delta X is the lateral movement or displacement of the jug weight. And we know from this triangle, GG star M triangle, we can just write GG star is equal to the GM times tangent delta theta. This is like the geometry. You can just easily write from the tangent, like the delta theta is opposite to the adjacent, and we arrange this one. So on the left hand side are the same. You can easily equal the right hand side, and just bear in mind the tangent delta theta is equal to delta theta in radians once the delta theta is very small. And we can just put like the GM delta theta rather than the or replacing with the delta tangent delta theta is equal to WG over W times delta X. Okay, it's like this one. So, and if you arrange the GM is a metacentric height, can be easily calculated by this ratio, is equal to WG is a jug weight over the total weight of the pontoon, including the jug weight as well, this capital W, times dx or delta x, whatever is fine, the lateral movement of the jug weight over the delta theta is the angle of the tilt that can be measured by the pendulum as the bottom of this pontoon. So we're just going to have this relationship. So if you just look at the laboratory experiment, so this is like the jug weights that we have, and this is like a pontoon, and this is a pendulum and a plumb bob, for example. We can see it here. We can just measure the angle of the tilt here in the laboratory experiment. We will see this one, and this kind of like the pontoon is a stable as a floating body over the water. So the center of the gravity of the pontoon can be increased if you're just gonna rise the height of the jug weight here. The center of the gravity can change from somewhere to like something like lower. We have like a 1, 2, 3, 4, 5, like the rows in the vertical heights from the bottom. We're just gonna change that one, and as you can see here, there's like an indents here, and you can, for every movement, you can just go to the left and right to just provide like the lateral displacement of the jug weight. And you know, for each height, as we said, you can just move it 15 millimeters intervals, and you can denote it by dx or delta x parallel to the deck. So you can just do this one as well. So this is like the test that we can just see if the jug weight is moving over the sail here, sailing part, how the tilting is calculated and how we can just calculate the stability of the pontoon by measuring the delta, the GM, metacentric height. And the tilt, delta theta, indicated by the plumb line that can be recorded from the bottom of the pendulum here. And the result can be plotted here so that you can just easily see how it goes ahead. The gradient of the delta x over the delta theta calculated. Just bear in mind the theta is in radius. And just bear in mind, if you're just going to substitute this ratio in this formula, and we know that like a WG and the capital W is like a total weight and is like a weight, WG is a jug weight. Here we can just easily calculate the GM. Okay, so let's look at some typical results. In the first column, you can see the height of the jug weight, in like the first, second, third, fourth, and fifth row. You can see here. And the second column is the corresponding measured height of the pontoon center of the gravity. For example, once it's like at the lowest level, 105 millimeters or 10.5 centimeters, the measured value of the center of the gravity, point OG, it can be measured like the 58.7. So the way it's been calculated here, there's in the laboratory, we'll see here how we can just calculate the point G. This is something that we can just see in the lab, in the laboratory. If we're just gonna hang around the pontoon about one specific point, we can just measure the plumb line above the base, and we can just measure it as the OG, or the center of the gravity, away from the base. So for any kind of the location of the jug weight, we can just have the corresponding the OG, or the center of the gravity. As you can see, it's increasing. What will increase in a jug weight with the 34.5 centimeters, and that one will be also increased from the 5.87 centimeters to 9.2 centimeters. And column 3, we're just going to use this kind of the ratio. We measure the dx, we know that one. And the dx, just bear in mind the last column, we're just going to move the first indent, only the 15 millimeters or 1.5 centimeters. And the delta theta, angle of the tilt, can be recorded or can be observed from the intersection of the plumb line with the pendulum at the bottom of the pontoon. That can be read from that kind of the points is starting from the 2.7 and up to the 7.5 degrees. Okay, so if you're just going to have all of them together, and you convert these degrees to the radians and you put in the formula, you can see the GM can be calculated as this one. Please just make sure you can practice this one, and you can just get these values. And if you can see any difference, please let me know so that we can just have a look in further details. And column 4, so for example, you need to just calculate the BM. The BM in this figure, it's just if you have an OG in column 2, GM in column 3, and the OB is the half of the depth of immersion. Depth of immersion here, how we can calculate that one. We need to just calculate the BM, and then we just need to just calculate the volume of the water displaced, and divide by LV, we can calculate the H, or in the experimental, we can easily measure it by tape measure, the depth of immersion easily. And half of that is the center of the pressure for the displaced water, and OB can be read. And experimentally, H is a 38.8 millimeter, and hence half of that, it's the OB is the 19.4, is the OB here. So, and once you're just gonna do this one, we have a few findings we can get it from here. First of all, experimentally, you can calculate the BM. So here you can see the BM for each level can be measured like this one. I mean, it's more or less similar, but the average value of the experiment is the 86.7 millimeters. But we know that theoretically we can calculate the BM by using this formula, second moment of the area divided by the volume. And if you're just going to do this one experimentally, we can just get to 87.4. There's a little bit discrepancies here. And that's because of the experimental error that we might have seen here. Okay, this is like one finding. The other one is that you can see once m is fixed, this one m is 6 here by using the formula that we use it here. And once all of the test here, the point the m is fixed and the point b is also fixed as well. Once we're just going to see the OG, the center of the gravity, increases in different levels of the jet weight, you can see the GM decreases as well. I mean, because this one is fixed, once it just goes up, the GM distance will just decrease because of that. And also one thing that's very interesting is that once you can see the angle of the tilt experience increases, angle of the tilt is here. So you're just going to see the GM decreases as well. So you can see the GM decreases here, and we can get the stability of the pontoon decrease once the angle of tilt increases. And based on this formula, we can see the GM decreases as well. And the other finding is that if you're just going to measure for each level, we can plot it in this kind of the graph. Horizontal is like a lateral displacement or position of the weight. For example, every the movement, we have a 15 millimeters, 15, 30, 45, 60, and 75. The first line, this line is for the lowest or the bottom, the row. And that one, this line is for the top row. And the vertical axis is the angle of the tilt that we can measure in degrees, for example. So this is for the maximum height, and this is for the minimum height. For the maximum height, we only have one movement. If you look at this kind of here we have a few more indents to just move, but at the top, we just only have one to the left or one to the right. Okay, so if you're just going to plot that one here, we're just going to see here. And obviously, anything in between will happen, a line will happen, something aligned between these two lines, obviously. But for each of them, we have one level more until we're just going to get to this one, that the maximum displacement is the 75 millimeters. So there are some other findings here as well. As you can see, for the highest center of the gravity, which is this one, the ratio is very interesting. The ratio of the lateral displacement for this one or this one is constant. It's just there's only one point, to be honest, here, and we cannot judge them properly. But for that one, we can say that the GM is constant. For even if you have any other points, it's just proof that it's all of them are through it's kind of a direct line. And similarly, for the lowest one, we can just have a better evidence for that. You can see the ratio of the dx or delta x over the d theta or delta theta is the same, is fixed. The slope of this line or the gradient of this line is constant. And we can say, for example, once this term, the second term of this equation is constant, the first term that we know is constant because we didn't change the WG or the capital W, all of them are the same. So obviously, once we have all of the right-hand side is the fixed, so the GM is fixed, and we have a very key the results here, and we can say the lateral displacement has no impact on the stability. But as you know, if the GM decreases, we know that the stability of the pontoon will reduce, and we can say the vertical displacement of the pontoon has got a major impact on the stability because of change in the center of the gravity. And we know if the center of the gravity or the GM decreases, the stability is reduced. So just bear in mind, if you have any element and you vertically move it over the ship, boat, vessel, pontoon, it can have an impact on the stability of the pontoon. But if you're just going to move it laterally, it doesn't have an impact on that. So this is the lesson for the pontoon. So we're just going to test this one in a laboratory experiment as well.